All right, welcome. Good to see some of you. Happy belated Valentine's Day. Happy on time President's Day. And again, for those in China, Happy New Year to all of you. So a lot to celebrate today, including proof by contradiction. That's the plan for today's class. So we'll be working with worksheet 8 for today and again on Wednesdays. We'll split this out over 2 days. So with that in mind, I just want you guys to know that originally there was a quiz that might have shown up in Canvas for Wednesday's class. There's no pre-class quiz on Wednesday, no video for that, because we're just going to keep on working with proof by contradiction. But I did add a survey up in Canvas. So here's our Canvas page. Here's our week 5. So I moved out some materials that might have appeared here. We'll get to them next week. But there's a link here that says early semester course evaluation. So this is not graded. It's anonymous, so I won't know who does it and who doesn't do it. That's I want you guys to feel comfortable sharing your thoughts. But I will say that if we get an 80% response rate overall from the class, then I'll add some additional points, 2 points onto your first midterm, which is a couple of weeks out. So please do take a look at this. So rather than a quiz before class, try and get this done before Wednesday. That would be great. Questions are really just like, how's the pace of the class going? What's been working? What hasn't been working? I think it's good for you guys to evaluate me on how things are going before I then get to evaluate you for the exam. Any questions about that? And then just remember that homework assignment. The next one is up, and that is due on Monday, a week from today. And I did make one change to that. One of the proofs that I had up was actually was a false statement. And so I corrected that. So just be sure that you, if you've downloaded this, you get a more recent version. I did color code. This was the one word that I had to change. That was even, which made that statement wrong. That should be odd. And now that you can actually prove that statement. Okay, any other questions before we get started? Okay, I hope you guys are warm, have a nice warm place. Okay, so first, just to kind of touch base about the reading quiz, which focused in on how we can negate statements. So we're going to be doing proof by contradiction. And so the main point here is going to be, rather than prove an initial statement is true, we're going to prove that the negation of that statement is false, okay, which is then logically equivalent to saying the original statement is true. So really the biggest piece in getting this process going, proof by contradiction, is being able to negate statements. And then based on the homework homework 2 that I graded last week, there were some issues with negating statements, in particular, how to negate there exists and for all statements. So definitely want to make sure that we review that. So one of the statements on the quiz was we wanted to negate for every prime p, the number p plus 1 is not prime. So remember that when we negate these, we just change the for every to there exists. So we change the for every to there exists, and then we negate the original statement. So if the original statement was p plus 1 is not prime, then we would say the number p plus 1 is prime. Okay, and then you can kind of do a logical check yourself to make sure that, okay, if this statement is true, this one would have to be false and vice versa. So if I can prove that this thing is not true, that would be equivalent to showing that this thing is true. Any questions about that? When we negate there exists statement like in B, then we should get a for all statement. And so here we would get for all integers, A, then we just negate the second part of that statement. And again, when we're doing negations, sometimes, excuse me, like it's not that awkward to put a not in front of something to negate it. In other cases, it's much nicer to avoid that. So rather than say not even, it is much more clear to say odd. So just keep those things in mind. I'm not saying you have to avoid no and not at all costs, just when it's really obvious to avoid using it, we should. Okay, and then for a conditional statement like this, P implies Q, then recall that the negation is an and statement. It would be that the hypothesis is true and the conclusion is false. So when we're proving a conditional statement by contradiction, that means we're going to start by negating that conditional statement, and it would look something like, suppose A squared is odd. So we leave the hypothesis alone, and A is not odd. We negate the other ones. We would say A is even. Okay, any questions about those negations? For the most part, they look pretty good. There were a couple of slip-ups here and there. So that's going to be our first step in this process. So we definitely want to make sure that we're clear on that. Okay, so the nice thing about, one nice thing about proof by contradiction is that we can use this to prove statements, not just conditional statements. We've been using direct proof and contrapositive proof, which are only used to prove conditional statements. So if I want to prove some statement, say P, doesn't have to be some conditional statement, then we're going to suppose the negation of that statement, go through some logical arguments, and hopefully arrive at some contradiction. So somewhere in our proof, we're going to see that some statement has to be true and some statement is not true, and that gives us a contradiction. So let me just say, as far as proofs go, not to put contradiction down before we spend a couple days doing it, this is my least favorite type of proof. It does seem just a little bit dirty when we're doing this. Maybe you'll get the same sense. So I would say, like, when this is avoidable, it's great to avoid it and do things directly or by contrapositive. We'll see today that there are just going to be some cases where we're just going to have to get our hands dirty with contradiction. Okay, so let's come back to this one in a second, how to do contradiction with a conditional statement. And maybe let's just start by looking at statement 2. In order to prove this, it would be nice for us to formally define what it means for something to be rational or irrational. So definitely store this definition away someplace handy, that we say a number x. So now it doesn't have to be an integer, right? So we have some real number x. It's rational if it can be written as a quotient of 2 integers. And what's really important here is that the bottom can't be 0, right? Or else that would be undefined. So it's not just any 2 integers, it's integers a and b, with the denominator b specifically not being 0. And so if that's the case, we say x is rational. If that's not the case, then it's irrational. So we don't really say things are not rational. The way we negate that would be with irrational. So let's say I want to prove question number 2 here, statement 2, which is that square root of 2 is irrational. Okay, so Okay, and let's just think, if we were to do this by direct proof, we wouldn't get very far because we don't even have a hypothesis and a conclusion, right? This is not a conditional statement. It's not an if-then statement. So for something like this, direct and contrapositive aren't going to work. And we don't have a conditional statement. So let's prove this using contradiction. So our original statement is up here. And what would the negation of that statement be?
Square root of 2 is rational.
So yeah, we would say that rather than saying the square root of 2 is not irrational. Yeah. So here is our claim. Square root of 2 is rational. So the way that proof by contradiction works is we're going to start by assuming the negation is true and then get some contradiction, right? Any contradiction that we can come up with. And this is the part that seems a little bit dirty here, is that we're just going to be kind of spinning in circles, possibly until we reach a point where we see this thing we claimed is true, but now we just showed it's false. There's our contradiction. And again, if we're not doing direct proof, or even if you are doing direct proof, it is really nice to indicate to the reader what technique you're going to be using. And then it will make sense why the very first line of my proof is going to be, suppose square root of 2 is a rational number. So there is a very clear kind of first step of this is what the first line of my proof should look like. The problem with proof by contradiction is we don't have a goal other than find some contradiction, right? In most of our proofs, we've been like, okay, I know my start is going to be this, my end is going to be this, and I have some room to kind of work and try and meet in the middle. With proof by contradiction, there is no goal here other than find some contradiction. And so that's why this technique is a little bit more free form here. So we don't have a goal other than can we contradict ourselves? So does anyone have a suggestion about maybe starting with this square root of 2 is rational? What might be a good next statement to claim as a result of this previous statement?
Use the definition of a rational number.
Yeah. So then we know that square root of 2 is equal to a over b, where a and b integers. And again, it's going to be nice to specify here, or not nice, it's required to specify here that in particular, the denominator can't be 0. Okay, does anyone have a suggestion about what we might want to do next? Yeah, and this is where it gets tricky, right? But like we don't have a goal here, so it's not really clear like what I'm working towards other than some kind of contradiction. So here's a nice little phrase that is nice to bust out in proofs. okay, without loss of generality. Okay, so this means, okay, I'm going to make some claim here that's going to come next that's really not going to affect. Yeah, so there was a suggestion, sorry, that I missed in the chat about squaring both sides, which is a great idea. We'll do that in a second. Yeah, so what I'm going to claim here before I square both sides is that usually when we write numbers as like a divided by b, we kind of write them in reduced form. So I'm just going to assume here that a over b has been reduced. So in other words, they don't have any common divisors other than plus or minus 1, which are divisors of all integers. So this little phrase here, without loss of generality, is just kind of bracing the reader. Like, I'm going to assume something, but it really doesn't affect any of the logic that came before or that's going to come next. Any questions? Okay, so let's take Jonathan's suggestion. So let's square both sides. So squaring both sides would give us square root of 2 squared is 2, and then we've got a squared over b squared. Any suggestions about what we could do next? So we want to get at some contradiction, and so far, the things that we've claimed that we can contradict is, well, we'd like to contradict that square root of 2 is rational. So far we've got, okay, that is some fraction, and all we know so far is that b is not 0. So if I can do something that shows that b is 0, that would be an example of a contradiction. I don't know if I can do that. Another thing that I've claimed so far is that a and b don't have a common divisor. If I can somehow show that they have to have a common divisor, that would be another contradiction. So all we're trying to do is contradict something that logically followed from our original assumption. Any thoughts at all? What can we do with this thing over here? That might lead us some way to think about common divisors. So we're saying a and b don't have any common divisors here. Can we get a b by itself or an a by itself? Yeah, almost. Before we get an a or a b by itself, let's maybe get the a squared or b squared by itself. So for example, I can solve this for a squared.
Didn't you like eventually get to a point where you're showing that a can't be an integer? It's like if you take the square root of those, wouldn't that work or not?
So if we take the square root,
Because that was one of our.
We'll basically get back to this point over here. So I think if we start taking square roots, we'll kind of get back over to this point over here. But you're right, we did claim that a and b are integers, so perhaps we could get that they're not integers. What I'm going to suggest here is let's see if we can get a contradiction for this. So we've written the square root of 2 in reduced terms. Now I've got a squared is equal to 2 times b squared. Right, so since a squared is equal to 2 times b squared is an integer, we know that a squared is an integer. And if a squared is an integer, or is a, did I just say an integer? An even integer. So if a squared is even, what does that tell me about a?
A is even.
Yeah, then a is even. I think we proved this earlier, that a is even if and only if a squared is even, something like that. Trying to remember when we proved that. So point being is that we're allowed to use results that we've previously proven as long as we refer to when we've proven them. I'm just trying to track that down. If anyone recalls that.
I think it was in like worksheet 2.
This was worksheet 4, question question 5. So we could say something like, we have proven by this statement, and this way it is, this was worksheet 4, question 5. You know, if the reader doesn't believe you, it tells them exactly where to go. That's a little bit more helpful than saying like, we have previously proven, because we have a lot of worksheets and homework assignments and things like that. But you can use results that we've proven in class together, or that you've proven on homework in the future. So that means if a squared was even in particular, this implies that a must be even. And so if a is even, then it can be written as 2 times some integer. And so we're kind of just going through some logical connections here, hoping again to get some contradiction. And so the goal here is a little bit more ambiguous. And when see where we might be able to get into a contradiction with the statement that was highlighted in yellow with where we're at here.
If a is even, then it's divisible by 2, right?
Yeah, so a is divisible by 2, that's right. So we've got that a is equal to 2k. Sorry, I used k over here, I realized. So maybe I should use a different letter. So you see any place where we could go back and maybe use this fact?
Can we square it and plug it back into that equation? Yeah.
Yeah, let's see what happens now. So we've got that a is equal to 2n. So we can use that back over here. So this would give us that a squared is 2n squared, which is equal to 2b squared. So now we've got that a squared is equal to 4n squared is equal to 2b squared. So that's equivalent to saying that b squared, if we divide both sides by 2, is 2n squared. And how does this get us to a contradiction?
Both don't both A and B have a common divisor then?
Yeah, that's right. So just to kind of tie that in, we're pretty much in the same place that we were with A, now with B, right? So using this same argument over here, we can see so here's another nice little thing to save you some trouble in writing proofs is that, okay, we don't need to go through this again because it follows the same exact way that we got a squared being even, implied a had to be even. So we can kind of just say it's similar to how a was even, we now see that b is even. So that means they share a common divisor other than plus or minus 1. So I'm just kind of highlighting the contradiction that we got. So sometimes when you're doing proof by contradiction, people put these little arrows in to say like, that's a contradiction. You don't need to do that. Just keep in mind, you might see that that's what it refers to. I don't really care what you guys put at the end. It's Valentine's Day or almost, you can put a heart over there. I don't really care. Just something that says, okay, now we're done. And so, yeah, that's how proof by contradiction goes. And I think for me, and a lot of mathematicians, I'm not alone, like the unsettling thing is if you feel a little bit weird about it, it's true. Like we don't have a goal here. So it almost just seems like we're just like doing a whole bunch of stuff and it seems kind of random until we get some contradiction. Like, why did I need to assume this? I really didn't need to assume this. I did it because I know what the trick is in this proof is that I want to get some contradiction. So it's kind of like there was no need to put this in here other than that I wanted to get a contradiction out. So it seems a little bit dirty to me, but that's the only way that I can think of proving this. At least doing it by some contradiction. There are other contradictions that you can get at. Okay, any questions? So when you have a statement such as this one, that's not a conditional statement. Right now, the only way that we have to prove statements, non-conditional statements, is contradiction. We can applied, the nice thing about proof by contradiction is that it can be applied to conditional statements as well. So taking a look at this one over here, we can certainly do this, or we could try and do this directly, because we have a conditional statement here where we have statement P is X is rational. And Y is irrational. So our statement P is an AND statement. It has two things in it. And statement Q is that X plus Y is irrational. And kind of the idea here is we're going to try and show that the negation of P implies Q is false, so therefore the original statement is true. So in other words, we're going to start, when we're working with conditional statements in doing proof by contradiction, by assuming the negation, which is going to be the hypothesis is true and the conclusion is wrong. Okay, so let's
If you can do that one by like direct proof or a contrapositive, if it's conditional, how would you know to go to proof by contradiction? Like, how would you know to reach for that when you had other tools to use?
Yeah, that's a very good question. Where am I here? Yeah, so let's take a look at this. And so, yeah, let's see what happens. Let's say we want to prove this. Using direct proof, which we certainly could do here. So we would start this by saying, suppose X is rational. And that Y is irrational. And then you'd hope to get to, therefore, X plus Y is irrational. And I think part of the problem here is that it's a lot easier to work with things that we know have to have a certain form, as opposed to things that we don't know have that form, right? And so what I mean by this is this part over here is very clear what this implies. Okay, it means we have this is equal to A over B, A and B integers, B not 0. And seeing this, right, is saying that Y can't be written like this. So we certainly could try and do this, in which case the goal is to try and show that this can't be written as some ratio of integers m over n or something like that. So let me just leave that outline there. But that's what direct proof would look like. So if you were kind of doing this, then kind of the next line would be, well, then we know that X looks like this and that Y can't be written like this. And it's a lot easier to work with. I know that X is equal to this, as opposed to work with things like Y can't be written like this. But I think let's kind of compare the structure of these different proofs. We certainly could try contrapositive on this as well, which remember would be showing that not Q implies not P. So in this case, we would say, suppose x plus y is rational, then we would want to show that the negation of this is true, and the negation of that would be that x is irrational, right? Since the original statement is an and statement, so its negation would be an or statement. So if we were doing this by contrapositive, we would start off by, let's suppose x plus y is rational, that's not q, and we're hoping to show that either x is rational or y is x is irrational, or that y is rational. And that's what this proof would look like. And maybe this is a little bit more clear on where to go next. And then from this point over here, we could, start to do something like this. And I think you probably could think about how to finish this up doing contrapositive. I think they're actually, you could connect these dots over here in some way. And so I think, this is important, and is that there's not one way to prove things. There's often many different ways to prove it. So yeah, just because direct proof doesn't work, we could do this using contrapositive or contradiction. But I do think it's good to have these different techniques down, since if you do hit a wall, then you've got another method to try. Since the goal of today is to practice contradiction, and let's see how this would look with contradiction. I think if you're trying to finish these up, I don't know where to go with this one necessarily. I don't see it. Maybe somebody else has a good idea. I think that this one over here probably seems a little bit more promising. I could see how to join up those statements. But let's see what contradiction looks like. We'll do this one. So with contradiction, again, we're going to start with assuming that P and not Q are true. So we're going to suppose the hypothesis is true, which was X is rational. Y is irrational. Okay, and in addition, we're now going to suppose that the conclusion is wrong. And the conclusion is X plus Y is rational then. So this statement, this first statement, is saying that we are going to suppose that P and not Q are true. Okay, so being that it's a little bit easier to work with things that we know are rational as opposed to working with things that are irrational, let's use the fact that if X is rational, we know that it can be written as A over B for A and B. integers be non-zero. Then we know that x plus y, similar being rational, tells us that it can be written as a ratio, as a quotient of two integers. So just to kind of keep tabs on what we're using, so we've used that fact, and we've used this fact, and so does anyone kind of see what might be a possible contradiction that we might be able to get to here?
Could you plug in the a over b for the x and the x plus y equals c over d?
Yeah, so let's kind of work with this assumption over here and the fact that we know that x is equal to a over b. So all of this together implies that x plus y can now write as a over b plus y, which we assumed was c over d. Good idea. Does anyone see why that might be useful in getting us to a contradiction?
You probably can then show that y would be rational.
Yeah, that's right. Exactly. I see that's coming in the chat too. That's right. So, when we were stating this statement over here, right, the one thing that we haven't used so far is that y is irrational. But we have assumed this. So if we can show that y is rational, that's a contradiction, right? We just need some contradiction. So if I can show that y is actually rational, that contradicts our very first statement. That proves that what we stated is wrong, and therefore that proves the original statement should be true. So how can we show that y is going to be rational?
By solving for y.
Yeah, we want to solve for y. So what we'd like to do in order to show that y is rational, keep in mind, we need to show that this is, can be written as some quotient. Where that bottom is not zero. So let's solve for y. We get that y is c over d minus a over b. And so if we put this over a common denominator, that looks like bc minus ab all over bd. And that basically puts us in this form, right? We know that the bottom is not zero because we know b is not zero and d is not zero. Okay, so this tells us And that's our contradiction. As far as whether that's any nicer than maybe what we could have done with contrapositive, yeah, I think if you could get contrapositive to work, then that might be a nicer proof here. I think the thing that's hard about contradiction, both writing a proof and reading a proof and trying to follow it, is that, yeah, is that there oftentimes they can be a little bit rambling because there is no real concrete end in sight other than can I contradict myself? Whereas with direct and contrapositive, you have a very clear goal to work towards, which sometimes makes it easier because you can start to work up from the bottom. We have no bottom to work up from in contradiction. Okay, so let me just say, like, on the homework assignment that you guys have due next week, it does say, like, prove this using this technique. So you don't get to choose the technique, and mainly this coming homework assignment is going to be practicing contrapositive and contradiction. On the exam, if I don't tell you you have to do it this way, you're welcome to choose whatever technique you want to prove things. And with that in mind, in my mind, I kind of think about direct being my first thought process, contrapositive being my next, and then if that doesn't work, I've got contradiction. Okay, so any questions about that? Okay. So I think let's give this one a next look, and let's try and see how things are going amongst you all. So this is a good one to try and think about in breakout rooms. So I want to try and prove this statement 3 using contradiction. And just to make sure that we're starting off on the right direction, right, here's our proof. We've got a P implies Q statement that we're trying to prove. So the negation of this right, is going to be P and not Q. So our kind of initial step when we're trying to prove a conditional statement by contradiction is going to be, let's suppose that P is true. And we're also going to assume that not Q is true. Which is xy is not irrational, which sounds better to say xy is rational. And we want to prove this by contradiction. So, right, there's, again, the goal that you guys have is to somehow go through some string of logical arguments to somehow come up with contradiction, and therefore our initial assumption couldn't have been right. Any questions before we try this out with classmates in breakout rooms? Let's see. Okay, So the rooms are open, and Lindsay and myself will kind of rotate through and make sure things are going okay. All right. Well, great. I think based on the discussions that I had, seemed like the goal kind of came into focus a little bit quicker maybe than it did when we just started the first one together. And it's pretty similar to the one that we did with the sum. And so like one kind of troubling thing that you might have with contradiction is that, yeah, we don't necessarily have like a focused goal other than we want a contradiction. But when we have statements like this, maybe like one kind of common theme that we're seeing is that it's really hard to show that something is irrational. But if we can show that it's impossible for it to be rational, then it is just as good. So that's where the contradiction works in here. So it's a little bit easier to work with things that we know can be written in a certain way, and then try and show that something can't be written in that way. Here's the kind of initial statement. I think we had this together. And so then from this point, it seems like, well, let's focus on these two bits of information. Which would tell us then we have x is equal to a over b for a and b integers, where they're both not equal to 0 in this case. Right, so generally speaking, it's just the denominator that we know is non-zero, but here we can also claim the numerator is not 0 because we know that x is not 0. And we also know that x times y is rational. So it looks like this. And in this case, it's possible that that is 0. So all we know for certain is that its denominator is not 0. So we kind of have used the two bits of information highlighted in yellow. And so really the only other claim that we have in here is this over here. So let's try and show that that is in fact not true. So kind of comes into focus now that we do have some goal and if we show that y is rational, then we've got our contradiction. So in other words, our goal here is to show that y, right, can be written like this. And so does anyone want to take control of the proof at this point?
Then dividing by x to get y alone.
Yeah, so then we can try and solve for y. That's right. So it makes sense that we would want to do this. And why can we divide by x?
Because we said that xy is rational and equal to c over d. So we can say that xy is equal, or xy divided by x is equal to c over d divided by a over b.
Yeah, and so, right, if I'm going to divide both sides of an equation by x, which it's an unspecified value here, just one subtle thing to note is that we can divide by x as long as x is not 0, right? So if we didn't know this, then we might have to worry about cases like case x is equal to 0, and then you wouldn't be able to do that. And then you would have a second case when x is not 0, and then we can divide by it. So just be mindful of that. It is important in this definition that our denominators are not 0 because we have this issue about dividing by 0. So you're totally right. We can divide by x. So one way that we could say this, and it might just be nice just to justify it. I know that you might get mad when I divide sometimes, but hey, we know that x is not 0, so we can divide by x. So this would give us c over d. Could write it like this. And I know some of the other groups did it by substituting a divided by b in for x and then going about it that way, which works too. So we can divide both sides by x. And this gives us 1 over x would be b over c. So probably various ways that you could get to this point over here. Okay, so that gives us y is equal to c times b over d divided by c.
Shouldn't that be b over a for x?
There's an a here. Yeah, thank you.
Yeah, okay.
Yeah, that's right. And there's an a there. Thanks. So now we've got this written as quotient of two integers, m and m. And what's also important to note here,
that n is not equal to 0.
that's right, that this denominator, we need to be sure that this denominator is not 0, which we know is the case because we know that a is not 0 and d is not 0. So then there's no way that this product could be 0. And that does it. Yep. But this little detail is definitely important to point out. We wouldn't want to say, well, look, we can write it as something over 0, so therefore it's rational. That would not be good. So yeah. Any questions that came up when you guys were discussing this? Yeah, so as we're out of time on this one. So yeah, I think next time we definitely will be able to get through these other proof by contradiction. So I would say, the homework assignment is up. Definitely give it a shot. So there are some kind of shorter questions like, give me the contrapositive of this, give me the negation of that. There are some that are, here's a proof, read the proof and tell me what's going on in the proof. That probably shouldn't take as long. And then you've got several proofs at the very end that say, use this technique, use that technique. So I would definitely encourage you to start getting going on some of those, and some will probably be easier than others. But if you have questions on the homework problems, Lindsay and I are around to help you with those. So just let us know. Otherwise, have a nice afternoon, and I will see you all on Wednesday.